for his mission. So, yep, same mission Michelle served in. So, yep, I won't get much sleep. Who would like to offer a prayer for us? Thank you.
Dear Heavenly Father, thank you for this wonderful day that we have to learn and to grow and to build relationships here on earth. And please help us at this time to be able to feel Thy Spirit and understand all the things that we need to learn today and to be ready for the exam. Please bless all of the teachers to be able to know how to portray this information to all of us for our understanding. Please help us that we can have a good rest of the day and continue to do Thy will at all times. And we leave these things in the name of Christ, Father. In the name of Christ.
Amen. Thank you very much. All right. So any comments about devotional yesterday from Elder Pace? It was so good it left you speechless. So, a couple things I liked. He brought up two things at the end about how to study the scriptures. One, to connect all your scripture reading to the Book of Mormon. Talked about the power of the Book of Mormon. Shared some quotes from past prophets and our current prophet about the power that comes from studying the Book of Mormon. Talked about how Henry B. Eyring has gone 50 years and has read the Book of Mormon, studied the Book of Mormon every day. It's really powerful. And then the other one about being humble and studying with a humble and open heart. He shared the experience when he was young and married. He would often pray that God would change his wife's mind and help her see the right way, which was his way. And he changed. And he talked about praying with a notebook and pencil, praying with an open heart and humbly saying, how can I change? What do I need to work on? And then he would take notes, and then he would pray some more, and he would take notes. And he said, those kind of prayers reach heaven. And I testify to you that they do. So, okay, any comments? Any more comments about the devotional? Okay. Got an exam coming up, starts next week, Thursday the 25th to Monday the 29th. Monday the 29th is a late day. If you start it after 11, it'll cost, on Monday, it will cost you $5. We only have 8 days of class left after today, which is kind of crazy. Yeah. And we're only covering, I don't know, we might only have 5 sections that we're covering. I think there's at least one review day at the very end. But we spend a few days on single value decomposition because it's a pretty hairy topic. Awesome, but hairy. Speaking of hairy, I've already talked about how to enter in matrices into Wolfram alpha, right? Using the syntax. Yay or nay? No, I thought I did early on, but I wanted to show you, oops. Sorry, I meant to pull this up before, my bad. So when you enter this in, it will give you a whole bunch of information about the matrix. So it will give the determinant right there, the trace. The trace is the sum of the diagonal entries. That's an important single value like the determinant to a matrix. It gives you the inverse, gives you the characteristic polynomial, which you read about for this section. It tells you the eigenvalues, tells you the eigenvectors, and it gives you, it tries to create the diagonalization. Sometimes you can't do that. We will talk about that today, well, more next time. But it has this decomposition that's really important, and the condition number. You'll learn about all of these at least to some extent, this one, except for the condition number. You've already learned about all of them except for this decomposition. So it's handy, like just to be able to enter that in and have it spit out all that information for you. So when you're doing stuff on your homework and you can't figure out, you don't think you did it right, put it into here, put it into Wolfram Alpha so you can quickly get some help. Okay, get some feedback. All right. This came up in the 5 o'clock class about an idempotent matrix. Someone said, well, shouldn't that just be the identity then? Because for an idempotent matrix, you can multiply both sides by A inverse, and then you'll get A equals the identity. It's true, any invertible matrix that is idempotent is the identity matrix, but there's lots of non-invertible matrices that are idempotent that are not the identity. So, and just wanted to clarify that. Hey, questions on anything coming into class today? Yes. No, there is no review for this exam. I include that in an email I sent out earlier today. You probably haven't seen it, but we do have review materials up on Learning Suite. There's a couple review sheets. There's 4 or 5 practice exams with keys. So yeah, so the material's up there, but because they shortened the semester by a week, one of the things that got cut out was the review day for exam 2. The Tuesday, Thursday sections, they didn't get a review day for exam 1. We were lucky that we did, but we don't have one for exam 2. So that's one reason I put over here, study for the exam. You should start studying this, this weekend from here on out, like get studying, because we're just going to be moving through new material, so you won't have a chance to catch your breath. So good question. Yes, Michelle? Yes, they sent out emails. You guys should have got an email about them. Did you guys get an email about Math Lab reviews? Yeah. So I don't know if they're done yet, because we're taking our test later than the other sections. So we're a little bit behind. So I don't know if they're done or not. So there's another question back there. Yes.
Yeah, I have a question. So like if A is invertible, then like how do we find like the eigenvectors for it? Because I thought to find an eigenvector, the determinant had to be 0, which meant that it wasn't invertible.
Oh, great question.
How do we know also that the like for A inverse, the eigenvalue is 1 over?
Yeah. So yeah. So that question for those that were online. Why does it make sense to find an eigenvalues and eigenvectors for invertible matrices? Because when we find the eigenvectors, we're trying to find the vectors that are in a null space, right? So the difference is there's A and there's A minus lambda I. So we're trying to find the eigenvectors and eigenvalues of A, but to do that, we create this new matrix, A minus lambda I, where we subtract off the, we're subtracting lambda off the diagonal. Right, and we've got a whole bunch of stuff. This will be non-invertible, okay? But that doesn't necessarily mean A is non-invertible. It might be. So if 0 is an eigenvalue, that means you didn't have to change A, and it still had a null space that was larger than 0. Still had eigenvectors. So it might be, but A minus lambda I is always, we're going to find lambda so it is non-invertible, and that's where we're finding the null space. Does that help? Okay, nice question. Okay, other questions? Yes.
And in the reading, it mentioned some rule that helps you factor lambda cube terms, and like I was not familiar with that.
Okay. All right. let's start off by solving some, and I'll take a look at the book and see what rule it is. So, was it the factor of the A term and the factor of the constant term, and you're finding ratios of the factors? Yeah, yeah, I can explain that one to you. But okay, why don't you guys go ahead and start working on these problems? Okay, so so you're going to compute the characteristic polynomial, the eigenvalues, and a basis for each eigenspace of A. So that's a basis for each eigenspace is an eigenvector for, but it might be more than one eigenvector. You might have two eigenvectors for, or three for a lambda, for an eigenvalue. And the algebraic and geometric multiplicity of each eigenvalue. So that's number one, and then do number two. If you finish 1 and 2, then you can try this other 3x3 matrix over here. I don't know if we'll get to this, but this illustrates something different that I want to, hopefully we'll talk about. So. Has anyone got one? I'd be willing to write up their work on the board. Sure, as much as you got it. All right, let's start going through this. So we've got the matrix. We want to find our eigenvalues and eigenvectors. First step, let's find the eigenvalues. So subtract lambda off the diagonal and find the characteristic polynomial. We do that by finding the determinant. So I'm just going to turn these into determinant sign symbols. Okay, so let's take the determinant of that. So she picked like this first row to expand out upon. So it was 1 minus lambda times the submatrix minus 2 times that submatrix. Works it all out and factors down to lambda squared 1 minus lambda. So this is one where, yeah, some things cancel out, right? Here you got like a 2 and this 2, they cancel out, the negative 2 lambda and the 2 lambda. So this one turns out to be pretty easy to factor down. But you can get some that are hard. And there is a, in Appendix D of the book, they do get, and you may have learned about this in your college algebra class. I don't know if they teach it anymore, or pre-calculus. But there is something called the rational roots theorem that tells you how to narrow down your search for roots when you're factoring down a polynomial, at least for rational roots. This doesn't include things like the square root of 2 or pi or I, but the rational roots. So anything that you can write as PQ or P and Q are integers. So if we have degree n, the rational root theorem says, you look at the first term of your polynomial and you look at the last term and you factor those. And any rational roots have to be of the form PQ, PIQ, or PI or QI, where the denominator comes from factoring out the coefficient of your highest degree, and the numerator comes from factoring out the constant at the end. So we're lucky that when we set up these, at least if you don't have any fractions, you'll end up with just a lambda. Like this constant will be 1. So you really only have to worry about factoring down this end. And so any of the factors, positive or negative, of this constant down here, they will be your possible rational roots. So when you're trying to factor these down, you don't know where to start, factor down this end. And start trying out those as your factors. So, but this one's pretty easy. So we end up with lambda squared 1 minus lambda. You set them equal to 0. We get lambda equals 0 twice. Right? This is the idea of algebraic multiplicity. That we didn't just get a lambda. We have a lambda squared. So there's 2 factors that have a root of 0. So this is the algebraic multiplicity here is 2. Okay. So one way to think about this is that if we have a square matrix, if we have a 3 by 3 matrix, then we're always going to have 3 eigenvalues, except some of them might be repeated. But we'll always be able to write down the 3 eigenvalues. So in this case, we'd write down 0, 0, and 1. Okay? So if you're an n by n matrix, you need to be able to write down the n eigenvalues. Just some of them might be repeated. So, and with repeats, you'll end up with n. And then we had one factor of 1 minus lambda, so we get 1 with an algebraic, an eigenvalue of 1, and the algebraic multiplicity of that is 1. Okay? So, questions so far? All right. So far in the process, just give me a thumbs up if you're feeling good, thumbs down if you're not so good, thumbs sideways if you're like, okay. Okay. Lots of thumbs up and a few thumbs sideways. Okay, let's finish going through this one and then hopefully we'll have time to do another one. Start solidifying. But if you did your thumbs sideways, you have questions right now we can go through. Oh, that's better. That's like more ideal. Okay. All right, so how do we go through and find how do we go find the eigenvalues, the eigenvectors now? We have the eigenvalues, so we go back to the original matrix and subtract off each eigenvalue and then find the basis for the null space. And the basis vectors for the null space are our eigenvectors. So we subtract off 0. Well, that's easy. It doesn't change the original matrix. So subtract 0 off. We row reduce. We augment it with the 0 matrix, row reduce, and we end up with this. We can go a little bit further if we you can subtract 2 of these and to get this to be 0, and then this is -2. So you can go a little bit further there. And what do we end up with? I think you end up with the same thing, right? So this is our free variable. So our third one is our free variable. So you can let it equal t. Then you can put everything else in terms of t. And yep, we've got it here. Is this what you guys got? Okay, very nice. Okay, so we have one basis vector for the null space. Okay, any multiple of this vector, if you multiply this matrix by it, it'll be 0. Okay, in this case, we go back to the original matrix because we subtracted off 0 as our eigenvalue. When we subtract off 1, we'll get a basis for the eigenspace, but if we don't go back to the original, we have to go back to the one where we subtract off 0. So yeah, here if we go up, I get 2 times 2, a -1 times 2, they're added together, that's 0 plus a 0. Great. Here I get a -2 plus 1 plus 1. Added together, I get 0. Here I get 0 minus 1 plus 1. I get 0. Great. I just checked. That's a nice thing to do when you're on the exam. Hey, does this make sense? Go back to your A minus lambda I matrix, which in our case was the same as A, and just check and make sure that it's, yeah, when you multiply it, you actually get 0. So this is an eigenvector, or any scalar of this is an eigenvector of the matrix. So we have for lambda equals 0, the eigenvalue with this is 2, a -1, 1. All right, what was the algebraic multiplicity here? It was 2. How many eigenvectors did we get? What was the dimension of the null space here? Just 1. We only got 1 eigenvector. We only had 1 free variable. So that means our geometric multiplicity is 1. Okay? So in this case, the algebraic multiplicity was not the same as the geometric multiplicity.
To get the geometric multiplicity, like you're saying, do we count the number of rows or columns?
No, it's the number of vectors. So here we just get 1. Right. So if you have 2 free variables, you're going to end up with 2 vectors. And so, yeah, you'll have like an S times a vector plus a T times a vector. Yeah, so then your geometric multiplicity would be 2.
Okay, I was confused a little bit from the reading because I thought when I was talking about that, it was like, was it R2 or R3? And I thought that like R2, R3 is the number of rows.
Yeah. No, it's the span of it's the dimension of the null space, which is the same as the number of vectors, the number of free variables, or the number of vectors you find to span your null space. So, okay, nice. Okay. All right, so what about lambda equals 1? We go to the original, subtract off 1 from the diagonal, we get a new matrix, augment to a 0, row reduce, and we end up with 1 free variable. You better end up with a free variable when you subtract off lambda. Otherwise, you picked the wrong lambda. You didn't find the right one. So if you don't end up with a free variable, you're in trouble. Okay? Because all the free variables we're trying to find, not free variables, all of the eigenvalues are the things you can subtract off and make it a non-invertible matrix. So you better have a free variable. So subtract it down. So you got this far, and then solved, put everything in terms of a free variable x3, called it t, and we get 1, 0, 1. So now, yeah, so now, Now, if you come back to this, the a minus lambda, a minus 1, if we multiply that 1, 0, 1 times this, we better get 0. We better get 0, 0, 0. And you can check it out. You can come over here, 0 times 0 times 0. When we do that dot product, here you get a minus 1, 0, plus 1, you get 0. Here you get 0, 0, 0. Great. Nice. So here, for lambda equals 1, we get an algebraic multiplicity of 1, okay? Because we just had 1 minus lambda was only a root of the characteristic polynomial. It's only a factor of the characteristic polynomial one time. And the eigenvalue associated with the lambda equals 1, 1, 0, 1 is, yeah, so this tells us the geometric multiplicity of that's also 1, because we only got one of them. Okay? And why do we care about geometric multiplicity and algebraic multiplicity? If they're always the same, then we can diagonalize, we can do really nice things. We can get all the power from eigenvalues and eigenvectors, working with scaling transformations and easy math. If they're not, it's not as simple. So, okay. All right. Other questions? So questions about this so far? Yes.
So to clarify, like under what conditions are the algebraic and geometric multiplicity the same? Like is there a pattern?
There's not a strong enough pattern that we teach it to you in this class, but we did teach you that it's equivalent to two things. One, it means it's diagonalizable, which we'll talk about next time. It's similar to a diagonal matrix. It also means that your eigenbases, all of your eigenvectors for the matrix, you have n linearly independent eigenvectors. Here we only have 2 linearly independent eigenvectors, but we're in R3. We have a 3 by 3 matrix. So we don't have n of them. We have 2. We need to have 3 of them. And if we have 3, then we can diagonalize, but we can't. So, the short answer to your question, well, the way we test to see if it's in this nice situation is we find the algebraic multiplicity and the geometric multiplicity. So that's the way we're going to find it. There's not a shorthand trick to tell from beforehand. At least we don't have enough to talk about that. Good question. Okay, other questions? Cambria? That's right. Here, let's do this other 3 by 3 that's already. Yeah, so 1, 2, 3, 0, 0, 0, 0, 0, 0. Okay. What are the eigenvalues of this matrix? It's a triangular matrix. It throws you off a little bit because you have so many zeros, but these are all zeros, so it's a triangular matrix. So it's just 1, 0, 0. So we have lambda equals 1, lambda equals 0, 0. So we have an algebraic multiplicity of 0 twice. Okay. If you don't believe me, you can subtract off lambda, and the determinant's just going to be multiplied down the determinants. You're just going to end up with negative lambda times 1 minus negative lambda, and you factor down, you just end up with basically the same thing you have over there. Okay. Let's look at 0. Let's try to find the eigenvectors for 0. So if I subtract off 0, I just get the matrix. Row reduce. Great, it's already row reduced. Okay, and so what does that mean? Well, let's translate this back into equations. X plus 2y plus 3z equals 0. I have 2 free variables. So y equals s, and I'll say z equals z equals t. I can pick whatever I want for those free variables. So I can rewrite x as x is a negative 2y plus 3 negative 3z, and y equals s, z equals t. Replace your s and your t, I'm sorry, your y and your z with your s and your t, and what do we get? Well, this will become a s here. This will become a t. So for s, I have a negative 2, 1, and 0. Those are the coefficients of all my s's. It's easier to see if I move this t over here. Okay. But this is a case where I didn't just have one free variable, I had two free variables, so I better end up with two eigenvectors associated with this eigenvalue. So here I grouped all my t's together. What do I get? I get a negative 3, 0, 1. So this is a situation where the geometric multiplicity is 2. I have two different vectors here. Both of these, I need both of these to create a basis for my null space. So then in this case, the algebraic multiplicity is 2, the geometric multiplicity is 2. Okay. And the geometric multiplicity can never be less than 1. It's always, you always have at least one of them. So you don't really get into problems until you start getting algebraic multiplicities that are 2 or higher. But we'll talk more about that next time. Okay, let's take a step back. Questions? Yes?
So does an eigenvalue of 0 always mean that the original matrix is invertible? I mean, it's not invertible?
Great. So that statement was, does an eigenvalue of 0 always mean that the original matrix is not invertible? Yes. So in the invertible matrix theorem that we keep adding statements to that are equivalent to being invertible, yeah, if 0 is not an eigenvalue, then it's an invertible matrix. And if it is, it's not invertible.
So that means that if there's an eigenvalue of 0, that means that whatever eigenvector that is gets squished down right?
Yes. Yeah.
Okay, so geometric multiplicity is basically how many dimensions gets, like, this is weird to explain. Like that, like the first matrix, the 1, 2, 0, minus 1, minus 1, 1, that will squish down to a plane. But the second one will squish down just a line, which is why the geometric multiplicity is 2.
Right. Oh yeah. So right. So the a minus lambda. So you have to think about the a minus lambda matrices when you think about it this way. But when you're looking at zeros as your eigenvalue, then they're the same, right? So yeah, here this transformation will end up being project everything down to a single line, right? So I go from R3 down to R1. So my geometric multiplicity is 2 because I've lost 2 dimensions. Yeah. And yeah, over here, with one of these, I project down to a plane. I lose 1 dimension. With the other one, I project down to a plane. And so I only lose 2 dimensions. So my total geometric multiplicity is 2. So I think that's right. I think that's a solid way of thinking about that. I know there's some connection there. Yeah, but that's great. Nice thinking. Okay, other questions? Okay, I know not everyone is super solid on this, so what don't you understand about these? Are you so lost you don't know what to ask? That's always a tough situation. Here, let's go there and then Cambria.
So then what will happen for this last one that we just did if plug in those lambdas is 1? Wouldn't you get a 0, 0, 0? So does that mean that like your vector would be 0, 0, 0?
Great, so let's look at when we subtract lambda equals 1, we get 0 here, 2, 3, 0, minus 1, 0, 0, 0, minus 1. We'd augment it with 0, and we would row reduce. And this tells me that x is a free variable. Okay, this 0, 0, 0, I have a free variable here. I can row reduce. It's easy to multiply this by 1 and swap those. So I get 0, 1, 0, 0. I can use this one to get that 2 to be 0, 0, and this one to get that 3 to be 0. So I can move that down to the bottom. I can multiply that one by a -1, and I can get 1. So you can believe me that we can row reduce it to this. So so this means that my x can be anything. So my x is a free variable, but y has to be 0, y equals 0 and z equals 0. So I'm going to end up with 1, 0, 0 as my as the eigenvector for 1. So I have one of those. So geometric multiplicity is 1, and it was a root one time in here. So the algebraic geometric multiplicity are both 1. Okay, does that help? Okay, nice question. Other questions? Dang, we didn't get to the rabbit and fox example. So, but we'll dive into that one tomorrow. So just really quick, like we're back talking about eigenvalues and eigenvectors again. The applications of these are so many. If you're using a matrix somehow, chances are eigenvalues and eigenvectors are going to help you out, or eigenvectors and eigenvalues of related matrix are going to help you out. Especially in decomposing matrices, one of the biggest applications is trying to do computations efficiently and effectively. And so there's a whole field of mathematics trying to figure out how do you work with these things in a computer and make sure they're stable and you don't lose information and all sorts of stuff. If we use an eigenbasis, okay, so let me be clear about an eigenbasis. So these two vectors will be an eigenbasis for lambda equals 0. Okay, this one vector will be an eigenbasis for lambda equals 1. Together, all three of these will be an eigenbasis for the whole matrix. Okay, and basis vectors always have to be independent, linearly independent. The book proves that all eigenvectors are linearly independent from each other. So you don't have to worry about, oh, well, what if this one's already in the span of this? It never is. Okay. So when it talks about an eigenbasis, it's talking about the eigenvectors that you get out. And sometimes they'll talk about an eigenbasis in terms of an eigenvalue. So this is the eigenbasis associated with lambda equals 0. That's the eigenbasis associated with lambda equal 1. But they'll also talk about an eigenbasis for a whole matrix, which is just all of your eigenvectors, the basis for all of your eigenvectors. And any big last things here? Well, we'll have to hit these next time. So, all right, have a great day.
So I guess